Hi, this is the third question in Sierpinski's book, 250 Elementary Problems in Number Theory. Uh, and this looks quite easy, and so I didn't actually um, I didn't actually practice it. So let's go. So how are we're gonna work out how to formalize the question. Uh, so how do you say? I mean, one way of doing it would be like this. We could say that for all uh, n, which is a natural number, there exists an n. There exists an n bigger than n, such that 5 divides 4 times n squared plus 1, and 13 divides 4 times n squared plus 1. This is, I mean, this raises an issue, right? I mean, because I don't mention the word infinity here. I'm just saying that there exists arbitrarily large positive integers n. So of course you could then, you could attempt to you could attempt to you create the set of all n with that property and prove that that set was infinite, but then that's some sort of fiddly statement. You've got to prove that some set is infinite if and only if it contains arbitrarily large elements. Probably there'll be some assertion to that effect in Lean's maths library. But I'm just going to avoid that problem completely and write the question like this. So what's the maths proof? Maths proof. I guess the way to do it, perhaps I should have come up with a maths proof before I started on this. The idea is, you see, if n is 1, if n is 1 mod 5, if n is 1, then 4n squared plus 1 is divisible by 5. So that means, and that statement only involves n modulo 5. So if n is 1 mod 5, and then 4n squared plus 1 will be divisible by 5. And now we've got to do the same for 13. And let me just switch my phone off. Now we've got to do the same for 13, and I guess 13, what about 4? N is 4. Oh, here we go. Oh, that's interesting. In fact, if n is 4, then 4n squared plus 1 is 65, right? 4 4s are 16, 16 4s are 65, 1 is 65, which is 5 13s. It's divisible by both 5 and 13. So if n is 4 plus 65 times t, then this will work. Great. So I think I want to do that as a sublemma first. So lemma divides of whatever, of cong 4. My claim is that I've got n a natural number. Well, let's have t a natural number. I claim that 4 times, what will this be? Let's go with 65 times t plus 4 squared plus 1. I claim that 5 divides this. 5 divides this. And 13 divides it. 4 times 65 times t plus 4 squared plus 1. Begin, end. So I need to split this, and now, yeah. So okay, so you can't see this because I'm only sharing my VS Code. But what I'm doing right now is I'm firing up a maths package. I'm firing up a maths package on my computer, and I'm dividing it by 5. There, apparently. let's use this. Apparently this works. Ring. Yeah, that's gone well. And now, similarly, I need to... So I'm doing 4 times 65 t plus 4 all squared plus 1. I'm working that thing out. And I'm dividing it by 13. And my computer algebra package says it's this. So we're going to use this there, and then we're going to do ring here. So that looks like that's worked. And so now intro capital N, and so now we're gonna use. So now we need to use. We need to find a t such that 65t plus 4 is bigger than n. That's the goal. And then let n be that. So why don't we just use, I don't know, why don't we just use 65 times n plus 4? That should do it. And then we can split it. Bingo. And let's just sorry that for a minute. And I'm hopefully, to do this one, we can apply this. Let's try that. Apply that. Yeah, that's done it. So all we've got left to do is prove 65. Does linearith do this? I'm not entirely sure it will do. Oh, it does. So there you go. That's the end of that then. So that's the best one yet. That's the end of this video. Oh, well, I guess actually, given that it was quite quick, I suppose one could really talk about set. You see, this is somehow not number theory, right? One could ask, you see, this is somehow an independent question. So let's have an example. Let's have S, a set of natural numbers. I claim that is it if we got an S dot infinite, is that a thing? We do seem to have S dot infinite, if and only if that thing there, the thing I proved, for all n in the nat, there exists some n bigger than n, such that n is in S. There. So that doesn't feel to me like a question in number theory. I mean, if we're lucky, library search will do it. It didn't do it, so there you go. I mean, certainly one could prove that. How long's this video been so far? Oh, it's only been 8 minutes. All right, you've tempted me. I'm going to try and prove it, because then we should be able to. So now this will need a name. So lemma arbitrarily large Kong. Arbitrarily large solutions, let's say. And now let's give this a name, infinite if arbitrarily large. There. So how are we going to do this? Yeah, I don't know. Let's leave it as sorry. And now let's deduce. Let's now answer the question. So we've got to prove that this set here, I claim that the set of n in the naturals such that this thing here, that thing there, I claim it's infinite. Begin n. So I'm using Lean's dot notation here. This is the idea. This is a set, and there you can see. There you can see I got both of the division symbols there. So these are things which look identical. Do they look identical? Can you see the difference? I mean, you can tell the difference if you hover over them. That one says, "Oh, I'm slash pipe," and that one just says, "I'm pipe." So this should now be. So now I should be able to rewrite infinite if and only if arbitrarily large. And then I should be able to, then library search should do this one, because oh, hard luck, what have I done? I thought this was going to be exact. Have I got it wrong? Well, it's exact this, right? Oops. Exact arb. Go away. Large solution. Yeah, okay. I'm quite surprised library search didn't find that. Maybe it somehow didn't see through the... If I did dsymp, and now I did library search. Yeah, now it works, so there you go. Yeah, library search didn't see through the set theoretic notation, and now I can remove dsymp. So the only thing... That's right, yeah, I've got one warning down here, so that's this sorry here. So how am I going to prove that? And, I mean, let's have a look. I've got to go to definition. What do we know about infinite? We just need to find some useful finite or infinite. That's good to know. I mean, that's another thing we could do, isn't it? We could try and prove that it was finite if and only if it didn't have some arbitrarily large elements. Let's search for infinite. Have you got anything useful here? And there's a lot of things about infinite down here. We really want to talk about an infinite set of naturals. Embedding of naturals. If it's infinite, there's an embedding of the naturals. An infinite set is non-empty. No kidding. A set whose complement is finite is infinite. Those are no good. Something bigger than an infinite set is infinite. Removing a finite set from an infinite set. Oh, here we go. Infinite of infinite image. You see, that would somehow work. That would do one way. It would be a bit of a bore. Infinite image if... What does that say? That says an injection applied to an infinite set is infinite. And the other way. Oh, what's this? Hello. That is one direction. Brilliant. That is one direction, I think. Let's try that. So let's split it. Oops, what have I done? Come back. Oh, never heard of it. Oh, set dot. What does that say? That says if I'm infinite, then for all n there exists... Yeah. So that will do it. So have we got... Let's try this. Have we got infinite if exists nat? Is that a thing? Oh, curses. That's a bit annoying. Yeah, that's somehow missing from the library. So this says for an infinite subset of naturals. An infinite subset of naturals is unbounded. Let's have a look. There's only one more mention of infinite down here. Infinite is bigger than any fin set. And what's this one? Whatever does this say? In a linear order. Oh. That's of no relevance to us at all. So it looks like one way is missing. So we could do the easy way. And this is the one with infinite as a hypothesis. So what was it called? Set.infinite.exist LT nat or something. Well, let's see how far we get. So, split, and then let's intro H, and then let's drag that thing there. Let's call that H again. Have H2 can be that, because H2 says that something's infinite. And now H2 and the goal look really similar. So maybe, I don't know, maybe I can just I hope they are the same. Yeah, they are the same. So intros, intro n. I mean, finish will probably do it, will it? Oh, it doesn't do it. I might. Maybe it's wrong. Intro n, cases h2n. So let's do recases h2n with whatever m hm. And then hm, and then h2. No, we've got two h2s, h3. And now I'm hoping that I can use, what did I just get? I just got an m, so I'm hoping I can use m. Yeah, this is fine. This is exact h3, comma hm. Okay, so that's one way. And now the other way, how am I going to do this? So I could do intro h. You see, what does this do? Contrapose. So now this says, you see, I wonder, so intro h, now can I do push neg? But I can't. No, so now I want to get, have h2, I want s.finite, library search. I claim that if it says not infinite, then it's finite. Okay. So in fact there's, right, so we can just rewrite, set dot not infinite. This MP just means apply an if and only if in one direction. So rewrite that at h. And now, you see, this is now a question about finite sets. So we can go back to looking at our finite thing, and now I think it might be better if I search for naturals. I can't. This is an annoying thing about VS Code. I can't work out if I've got to copy that natural there, and then I want to search for that like that. Oh no! I don't. No. That's not what I want to do at all. I just want to find it in this file here. There. So where are some statements about naturals being finite? Let's see what we've got. Embedding of nat into an infinite set, that's useless. I want finite sets. The naturals less than a finite, the naturals less than or equal to a finite. Yeah. Interval, this is the interval, that's just the naturals less than n again. Oh, what's this? Find range greatest subset. Is that useful to us? Maybe not. Is that it? That is a shame. So we don't know that a finite set of naturals is bounded above. I know what we could do. We could convert it to a fin set. We could convert. We've got a finite set of naturals. I bet we could do this. Let's define S2, a fin set of naturals to be. I wonder how I'm going to do this. Finite. It'll be called something like finite to fin set. Here we go. Set dot finite to fin set. What does that want to eat? That wants to eat a proof that it's finite, and so that was H, I think. Oh, def. It's let. And how's that gone? Great. So now I've got a finite subset of naturals. And now I would imagine that there'll be some finset.sup or something. Have h2. I claim that there exists some b such that for all n in S2, n is less than or equal to b by library search, hopefully. Oh, come on. Really? So let's sorry that. And now this will do it for us, right? So now I can just do cases H2 with NHN, and I can use N, and now I somehow need to use, does finish do? Let's just check I'm on track. I think finish might not do it because it might not know the difference between S and S2. Why don't I do this? I claim that have H3, I claim that for all naturals, I claim that N is in S if and only if N is in S2. And is that REFL? No, it's not. So that's something else I've got to deal with as well. So there we go, we've got that. And so now I can rewrite, H3 at Hn. No, I can't, apparently. Let's try. Is it because I'm rewriting under a binder? Oh, what? Simp only. Can I not do this? No, it won't let me do it. Hard luck. Well, let's take it apart anyway. So intros at NHN. And I've got to show that N is... So, I can keep going. So H, where am I up to? H4. And so now I've got N is in S, and now I can rewrite H3 at H4, I should think. N is in S2, and so now, why is that problematic? And now I need to use Hn, so specialize Hn, and we want an N and an H4. And so now I've got, there we go, and there's my contradiction, so Linarith will do that for me. So that is nearly the end of the proof, but I've got this one problem left that says if I've got a finite subset of naturals, then a finite subset of naturals has an upper bound. And I guess, is there finset.sup? Use finset.sup. Is that a thing? Oh, there's a finset.sup and a finset.sup primed. Finset.sup. Can I do finset.sup S2 id? How about that? Will that work? There. And now intros. And now can I do library search? How long is this thing? Where am I up to? Oh no, I'm over 20 minutes. I should really think about stopping because this really wasn't. So now I need to know the API for this sup. So finset.sup, let's go to definition. Boom. Sup empty, sup cont, sup insert, sup map, sup singleton, sup union, sup let if. That looks good. Is there really not a sup? I just want LE sup. Is that not a thing? That's what it should be called, right? Sup LE if. Oh, but sup LE. What? LE sup. There it is. Why am I even in here? I know exactly what it's going to be called. Apply finset.le sup. What does that do? Oh, it fails. Hard luck. Oh, it wants the... Oh, that's... I wonder why that fails. Can't unify that. It wants a proof that... So let's put H in. Oh, there we go. Great. Sorry, it's complaining... Oh, there we go. That's... I'm done, right? Yeah, I'm done. So there you go. So that was like 8 minutes proving the question and like 15 minutes wrestling with infinity. But I think that's right at the end of that. And let me just be clear what we've done here. What did we actually prove? But there we go. We prove that the set of natural numbers such that 5 says such that, and the other things that look the same say divides. The natural numbers such that 5 divides that and 13 divides that is indeed an infinite set. Thanks for watching.